Payam is an Associate Professor and Associate Dean, International Western Sydney University. Associate Professor Payam Zekavat joined WSU in 2017 to enrich university's profile in the area of building surveying. His research and teaching mainly covers compliance in design and construction. Payam's research is interdisciplinary in the sense that he looks into the prevalent issue of non-compliance from multiple perspectives of policy and statutory requirements, advanced building technologies, as well as safety and professional obligations. Payam collaborates on different matters with a network of stakeholders, including building regulators, local councils, and designing building practitioners. Payam is presenting tonight to share the findings of a recent project funded by the Centre for WHS to evaluate the safety of the use of non-destructive digging on asbestos contaminated soils. The study was aimed at providing scientific evidence to support the granting of an industry-wide exemption for the application of high-pressure jet on asbestos-containing soils, which is currently prohibited. Please welcome Payam.
Jason. Look, early warning, I'm not as good presenter as Jason is, so apologies in advance if I cannot keep up to the quality. So thanks for the invitation. I really appreciate AHCA's opportunity for us to present the finding of our research. Look, big thanks to Center for WHS for funding the project. EDP partnered with us in the conduct of the research. Few people in this room also were engaged, and without them, this project wouldn't have been a success. Look, Jason, Carl, Nigel, John himself. Am I missing anyone? The big name, Kim Fenia. She's not here with us, but without her, I think we wouldn't have done the work as smooth as possible. And I missed her. Her also was instrumental to our research design and delivery of this project. Look, moving to the project, the part it relates to your guys' expertise is exposure to asbestos. And we spoke about how serious that problem is. And a quiz question, do you know how much was paid by the James Hardy's compensation fund last year for the asbestos diseases, roughly? In terms of compensation paid to the people, not James, the funding, the compensation fund. Have you? I might be looking at the wrong statistics, but the foundation, they claim I looked at the financial report. They claim that they've paid $150 million in terms of claims that have been made last year, 2022. So it's look. That's the scale of the problem with asbestos. And look, the site that we investigated, and I talk about the history of the site, people even didn't know that asbestos was there. So Parramatta City Council accidentally actually realized that there was a big chunk of asbestos deposited on the site. So the asbestos exposure, and what causes the exposure in our case is disturbance of that contaminated soil through high pressure jets, so non-destructive digging. So we try to understand what is the impact, what is the risk, and if it can be managed or not. We've talked about the scope. So just telling you about, we originally aimed just to measure the risk, but as we progress, look, in the design stage of the research, we realized that we need to expand it to cover other stuff like cross-contamination, the management. If the risk is low, what would be the controls that needs to be taken into the account, decontamination itself. But today I only concentrate on the exposure itself, all right, through the disturbance of the soil. What is non-destructive digging? In simple word, compared to mechanical excavation, when you loosen the soil by the impact of a mechanical, that excavator. In our case, you loosen the soil using high pressure jets or high pressure air, or even with pure vacuum. So as long as you can loosen that soil, you can vacuum it. What's the advantage? I'll probably talk into advantages a bit later. How it works, you can see in the video, we've put some footage from the actual experimentation that we've done. You loosen the soil, there is a suction, they actually called vacuum trucks. It sucks everything in, and as long as there is no asbestos, apparently it's very practical when you have underground assets, where when mechanical excavation is a big no-no, because you are going to hit work on around a live cable or some underground asset that you don't want to damage. That's really the solution. But becoming more and more prevalent, specifically a lot of NBN work, a lot of, when I was talking to NDD providers, a lot of Tlesra assets already underground, so excavation around those assets is also a big deal. So there is a demand for working with NDD more and more frequently, but we know that it's very likely that you find asbestos almost everywhere across cities. So this research tries to address one regulatory ban. We've talked about, Jason pointed to a few clauses in the regulation. Clause 460 prohibits application of high pressure jet water spray. That's the wording of the regulation on asbestos contaminated soil. So regardless of how good, how effective this technique is for excavation, you can't apply it, you can't implement it when there is asbestos. So the idea was that to see if the ultimate goal is to see if that regulatory ban can be relaxed. But at this stage, the idea was that let's understand the risk. Let's see what's the exposure rate and how we can manage that. I talked about water excavation, air excavation, and then vacuum excavation. In our case, the soil was loosened with high pressure jets. Water gun applies the pressure. It's called gurney when people in the industry use that. The technical word we used was water gun in our report. We use water jets simultaneously for high pressure water spray. Vacuum excavation, so the same thing. You need the high pressure to vacuum whatever has been already displaced. It's very precise. You can aim exactly where you want to dig. So it's a big advantage that you don't have with big mechanical excavators. It's safer in a sense that you don't have a big machine moving around. In the context of asbestos, we studied that. Comparing to literature, mechanical disturbance of the soil releases asbestos, and as simple as driving a car on asbestos contaminated soil release asbestos at a detectable level. In our case, and I'm jumping into the results somehow, except one exceptional case, the rest of experiments, we didn't have the asbestos reading in our air monitor up to the reporting level. So nothing was reportable. Everything was under 0.001 fiber per milliliter. Environmental friendly and high efficiency. Again, efficiency in terms of when you consider the context, when you have some barriers, when you have obstacles that you need to work around. What was our methodology? Look, there was a lot of factors that played, and we needed to shortlist them, narrow it down to a few factors, the independent factors. And what we ended up working with was the truck type, the water pressure, and the excavation pattern. So digging a trench or digging a wide and a broad, shallow square, or later we realized that when you do the digging, you ended up with like a wall of soil that you need to destroy. So that was our third type. So digging pattern, pressure, and truck. Pressure, I need to talk about it here. Majority of the trucks that we studied, and two types of truck that we worked with, the pressure it's not as easy as adjusting like a knob and you turn it and it adjusts it. It's usually a tap that you just play around with it. And it's not, look, there is a pressure gauge, and the pressures that we read is the average of that pressure gauge on the machine. But it's not really a big flexibility in terms of working with pressure with those existing machines, or at least the machines that we work with. But the highest pressure we work with was in the range of 3000 PSI, which is relatively high. They don't go beyond that because it damages the pipe. That's against the purpose. You don't want to damage the underground utility. So usually, for your knowledge, the range that is very typical is 2000. Even 1500. Below 1500, it would be very difficult to dig. So they usually set it between 1500 and 3000. So when I talk about high pressure, regulatory wise, all of the pressures that we work with was high pressure. In this context, 3000 is high pressure. When I talk low pressure, I mean 1500 to 2000. All right, 2200. So we worked with two levels of pressure, 3 digging pattern, and 2 truck types. What we studied, and I'm going to present, is the estimation of airborne asbestos fibers, the liberated fibers. We also studied the splatter, and it was really necessary to measure the cross-contamination. So it's not just the exposure, it's the cross-contamination. And interestingly, that's actually the main risk, the major risk in terms of working an NDD around asbestos contaminated soil. So managing cross-contamination is a big deal. And to manage, to track a splatter pattern, we use dust tracking. So we use those dust tracker in conjunction with our air monitors. But I again need to highlight that it wasn't supposed to replace that. It wasn't supposed to actually replace the reading of the air monitors. Air monitors are our main principal source of data for the findings here. And I'll show you how dust trackers eventually helped us to validate the models that we developed for our splatter. So it was actually giving us a continuous source of a stream of data that enabled us to do some sort of modeling. Now, look, remember in COVID time, everyone tried to model the sneeze. So everyone wanted to see when someone sneezes, how those water droplets scatter. We now have a model for that, for NDD. So we can exactly predict, if you give us the pressure, soil type, we can exactly tell you how big that dust cloud and the splatter would be. What was the use of that model? We can tell you exactly how big the shielding need to be to confine the cross-contamination. We did look, in my introduction, you've heard about, I like working with sensors, and other than air monitors and dust trackers, we used a lot of other sensors, like a slow motion camera, 4,000 frames per second. So that was one to see how things happened. Thermal camera. Water is, like, in terms of the thermal properties, is different to soil. So we were able to track the droplets. Normal cameras and things like that. So a range of cameras with the actual data were our source of data stream. The site itself, FSCAR site in Granville. It used to be a playing field. Back in 1920s, it was used as a rubbish landfill, as a rubbish tip. And you know, with rubbish tips comes cockroaches and mouses. So the simplest solution was to set a fire. So people used to set a fire, and when you read the council minutes, there has been a lot of reports about the fire, and asbestos being good in fire. It's not minuted, but one of the reasons we believe asbestos waste, like construction waste, or asbestos in bulk was deposited on site was to manage those kind of fires. And there are minutes from the Council in 1937, the solution that they had was to fill that depression as quick as possible. So they asked for more waste, kind of send an invite to other councils to send the waste. And when the spot that we dug was actually construction waste, was mainly construction asbestos contaminated, like asbestos containing material, ACM. We picked this corner, the mound here. The actual mound that was sitting next to for the spectator, next to the playing field, was actually from asbestos contaminated material. So it was really, in many cases, and I have the percentages in terms of soil report, we had up to, I think, 3%, 4% in one case, one of the samples, friable asbestos in bulk in that area. And not just EDP sampling, there was other reports that we rely on to pick which area is the most significant. And northwestern corner was a really significant part. We ran the data, the experiments in parallel with a redevelopment project. The story how they found out there was asbestos there. Parramatta City Council wanted to install a scoreboard. So they dug a hole for the scoreboard footing, and they realized that there was a big problem with the asbestos. So they actually accidentally found out, and then they went through the redevelopment. Good thing about this project, again, we have an on-site containment cell, so it made it very easy for us to tip the slurry, the excavated material on site. We also tip off-site. There is only one facility in New South Wales that accept asbestos in its slurry, liquid asbestos waste. So we had to work with them as well, clean away in St. Mary. Too much. Okay. We started with enclosure, a bubble. We ran our test inside the bubble, the early one, to make sure the exposure is not significantly high. Later experiment, when we had our reading and realized that it's manageable, we came out and tried to see if it can be managed in open air. Interestingly, and many of you would know that, look, inside the bubble, we had negative air unit, but we didn't turn on the neg air during the excavation just to replicate the worst case scenario. And outside experiment where we had a very gentle air movement, a breeze, it helped actually with dispersion. So I will show you the results. The outdoor experiments actually recorded a lower number of fibers on our membrane compared to the internal indoor experiments. The bubble itself, we had 2 cells in the bubble. After each experiment, if the exposure was about reportable level, the airborne concentration was above the reportable level, we turned on the neg air, then we did the clearance check to make sure it's ready for the next round of the excavation. 19 experiments in total, 10 inside, 9 outside. I think it's around, show the location. This is our bubble, cell 1, cell 2, and those that has been conducted outside. You probably can't read the numbers, but it gives you the actual air monitoring numbers. Except experiment 1, which I will talk about, the rest of the experiments, we have 3 exposure monitors on the NDD operator, on the NDD, the laborer, the assistant, and on one of the researchers. 3 background air monitors around the excavation area, and 8 control monitors across the sites. In the 19 experiments that we ran, all of the readings was below reportable level, except 18 experiment, I should say. The first experiment was an exemption. I tell you what happened there. Only 1 air monitor recorded 0.05. Anyway, the first experiment, what happened? The idea was, let me discuss the air monitoring. I think it's something interesting for you guys as well. One of the challenges we had was to make sure the data, the air monitoring data that we collect is reliable. And you would know that how much air you suck in is a key, and for how long actually the experiment, the monitoring goes on. So we had a discussion with a few of the colleagues. We ended up setting 400 liter for the amount of air that needs to be taken in. And given the productivity of the NDD excavation, we ended up running 90 to 100 minutes of actual excavation. Each experiment took around 2 hours from the start. There was some glitches in some of the experiment. For example, the pipe is very likely to clog if there is a big chunk of stone or a big rock that is sucking. So there was like 5-minute, 10-minute interruption for the operator to clear that blockage and things like that. But there was at least 100 minutes of active digging. And look, the good number, 400 liter was our threshold, the number that we ended up working with. We set 4 liter per minute in terms of the flow rates. And each experiment was run for actual 900 minutes of actual excavation. So data collection, I don't bother with the list of the sensory data that we worked with. I already talked about it. The slow motion camera. We had a drone to have a bird's eye view. We had the air monitors, the air over camera, that GoPro kind of camera on the operator. What else? The air monitors on the operator in the breathing zone of the operator. The air monitors around the excavation area, 3 of them, the background monitors, and the control monitors. Another important fact about this site, we have a childcare center, the opposite side of the street where we installed our bubble. So we needed to be very careful about that. So we had actually 3 monitors installed here. The childcare center was here. So we had 3 monitors installed for the control check to make sure the exposure is not high, and none of them were actually concerning. Dust trackers. So each station, data collection station, we had an air monitor next to a dust tracker, just to make sure we can have a continuous reading of the the splatter. You can see here, for example, we can actually record it. We have a synced video with, and that's an example, with the air monitor, synced with the air monitoring data in terms of the directional work of the gurney. And we were able to actually track how that reading peaks and fluctuates as the operator maneuver the gurney. Look, apparently different direction depending on the dominant direction of excavation. You would see that this is the time, the clock is the time, and this is the concentration that was read by each of the air monitors. So it actually helps us map the splatter size and intensity, and we assume that the dust cloud is contaminated. So that was the assumption we had. So whatever, as long as the dust trackers read something, we assume that it's contaminated. Analysis of the results. The first experiment, I need to talk about it. First of all, because the report, all the air monitor results were, when it's under 0.01 fiber per milliliter, we had to work with another variable, and to replace that, to be able to do some sort of analysis correlation, we worked with number of fibers per 100 fields. You know, when you use your membrane under microscope. So we started working with that because that was the only number that we had that we could work with. So all of these reports are based on that fibers per 100 fields. The idea was that we complete the contaminated soil experiment, and then we go and work out ACM. If you apply high pressure jet on ACM, what would be the impact? Unintentionally, it was unplanned. The first experiment, in the very surface of the experiment, after we removed like 20 mil, 20 centimeter, we exposed a very thick layer of compacted ACM. And by compacted, I mean it was ACM material that was kind of glued to each other. We don't know what that glue was, but I can show you a few of the photos. Yeah, that's the layer I'm talking about, that white thing. So we ended up applying the high pressure jet on the actual ACM material. And the result, as you can see, was concerning. Still was under the 0.1 threshold that is the trigger for the high exposure, but concerning, definitely higher than working with asbestos contaminated soil. So the differentiation is that when you have asbestos contaminated soil, the risk is significantly lower compared with applying your high pressure jets on asbestos containing material. And you can absolutely see that here, how different, like something around 2-3 fibers per 100 fields suddenly jumped to up to 30 fibers per 100 fields. So keep that in mind. It's a differentiation. So asbestos containing material, it's definitely a different level of risk and needs to be treated completely differently to asbestos contaminated soils. So keep that in mind. This is an example of combining our air monitoring data with our dust trackers. So this is a little bit of AI and machine learning. So we try to correlate the position of the bystander and the reading. So each of these is 90 iteration in each location. So each column is 90 iteration. This line is 90 iteration, and we connected the dots. And we've iterated that. We tried to kind of fuse the data from air monitors and dust trackers and try to come with a number. And when you do that, repeat it, the machine start learning and reiterating, coming back to the same pattern. You see that it's converging. And the convergence would be around 2 fiber per 100 fields. So like if you want to have a number in terms of if you apply high pressure jets in a severely contaminated soil, the number you expect is probably around 2 fibers per 100 fields. So that's the very conclusion of this research. If collecting all of the data, if you want to come with one number, it's 2 fiber per 100 fields, combining whatever data we had. Going back to experiment 1, we also send the samples for SEM to make sure it's asbestos, and you can see it's like 100%, 70%, 100%. It was actually asbestos. And the level of contamination, 2.2 percentage weight. So it's significantly high. This one was ACM in that particular example. Cleaning, decontamination. We took samples from the filter sample. Each of those trucks have a HEPA filter, okay? And we took samples from the HEPA filters as well. Asbestos was still present in the HEPA. So I need to explain. The air, when it's sucked, it goes through the tank where the actual heavier particle separates. And then the air goes through a cyclone centrifuge, and then goes through your HEPA filter, and then goes out through the exhaust. We have an air monitor on next to the exhaust. The reading was not concerning, but we found fiber in the actual filter, in the HEPA filter. Cleaning of the chamber itself, the filter chamber, was effective, but the cleaning of the pipe, even after flushing few times, we cut a cross section of the pipe, send it to the lab. Asbestos was still present. So it's probably the material of the pipe. So again, a very brief recommendation out of the research was that if you use those equipment for asbestos work, it probably needs to be dedicated to asbestos work. it cannot be moved from one project to another because decontamination is almost 100% reliable. Decontamination is almost impossible because you can't check the internal circuit. So that's one other finding. And again, decontamination and cross-contamination was really critical. I gave you an example of the slow motion analysis that we've done. Here is where we trace one particle. And I think it's, you see that that's water splash goes up, and then it's three-dimensional analysis. So the, and I forgot to mention Ehsan, by the way, when I was mentioning people. Ehsan was my postdoc helping me. This is Ehsan's work. Sorry, Ehsan, I forgot about it. So this is how we've done it. That's the actual modeling that we've done. Another one regarding the drone footage that then was overlaid on what we had to our slow motion camera. And we had our model. Like, for example, in our modeling, we now can apply the impact of wind. If there is a moderate wind, what would be the impact of your splatter size? So that's and again, a number, if you want to have a number, 4.5 meter is a rule of thumb out of our experiment in terms of the size of your cross-contamination, the dimensions of your splatter. A little bit, again, a video about the modeling itself. The green, the yellow ones, no, the red ones are the actual data. The green ones are the simulation. And when the simulation map on the drop exactly on the actual data, it would be shown as red. Am I right, Essam? Yeah. Yeah. So the red, the more red this graph is, the more accurate it is. Just the way to read it. So now we are able to model the dust tracker, the dust cloud. Well, I'm keeping, look, trust me, this is the validation that we've done in terms of correlate, matching what we had against the data that we, and you see how the models start converging in terms of the reading of the next iteration. An example of our thermal camera, how we've been able to track the darker, the colder, apparently, and you can assume it's water or a dust or piece of mud or whatever. Results. High pressure and low pressure. Let me put it this way. The factors, the independent factors that we studied, they had an impact together. So when you combine 2 or 3 of them together, you see an impact. When you study each one of them individually, you don't see a big impact. So, for example, truck combined with high pressure, you see an impact. But pressure itself, you probably only see 10%, 20% impact. And I talked to you about it. The most important thing here to see is the impact of air movement. That's what I put here. When you don't have air movement, in average, your readings are higher. So regardless of the pressure level, in average, if you have a very moderate air movement, and if you are familiar with Trump's work, the godfather of asbestos research, he had seen exactly the same thing. He reported exactly the same phenomenon. If you have a moderate air movement, it helps with the dispersion. Yes.
The truck is a variable. What's the variable there? Is it the amount of differential pressure of the vacuum?
Look, first of all, I had the very first question in my mind is when we started picking that as a factor, I thought they are the same. What we realized, first of all, the design is the same, the way it works, the mechanism is the same, but the dimensions are different, for example. The way the pressure is controlled is different. We were not able to identify what exactly is in that truck that creates a difference. But eventually our results show that when you move from one truck to another truck, the results are different. Same operator. We use 2 operators but they were relatively the same in terms of years of experience, even in terms of operating the gurney. We did check that. We had to use two because having one operator for 10 days, we did this in 10 days. It was a physical task, and one of the operator lost his mother-in-law during the experiment, so he had to leave. So we had to replace him. We had no other choice. But Ehsan did compare the operators. They were almost identical in terms of the way they operated. Even we checked the productivity. We checked the way they start digging. They were identical. But look, it wasn't the operator. Yes. Yes.
So we're looking at something being blasted and then thrown in the air. So was it considered perhaps the amount of velocity and volume as opposed to pressure? And then could you then use the existing information to see if it's better correlated to the velocity and pressure rather than the truck? Because how was the pressure of the trucks between each other ensuring that it was the same pressure? How they calibrated things like that? Just food for thought.
Yeah, velocity, you mean the jet velocity?
Yeah, jet velocity.
Yeah.
Does that make sense?
Yeah, I understand what you're talking about. Look, we haven't done that, to be honest. We haven't looked at it.
Food for thought to see whether it actually be a better measure. Yeah.
Yeah, I'm just thinking how we can look. We can calculate. Look, the problem with the pressure was that, again, when you ask the operator to set the pressure on 3,000, it's not constantly 3,000. It drops, moves up, comes back. So it's an average 3,000. It's really an instinct of the operator. They only have a tab to play with to adjust it to 3,000. And they were really skillful operator. You would be amazed to see how they adjusted in an angle, and it gives you an average the pressure you ask them to give it to you. But look, that's the problem with the truck. Another difference in the trucks, even in terms of adjusting the pressure, they had two different. One was before the gauge, the other one, the pressure tap was somewhere else. So
I'm thinking with respect to like the pressure of the vacuum as well, like how quickly that moves.
yes,
So where you're blasting relative to where the vacuum is positioned,
Yeah.
it's going to have a massive
Yeah. Look,
difference in
exactly. Look, you know that telescopic boom? If the telescopic boom is, look, when we were outdoor, we've been able to put the telescopic boom exactly on the excavation spot without any extension. So in those experiments, actually the splatter was smaller because the operator was able to handle it precisely. It gives us the idea that the difference might be because of the extension, the pressure that you mentioned, because the inside experiment, we had to use 40 meter of extension pipe. And we thought it may impact the pressure, it may drop the pressure. The only way we could compare it was to ask the operator, did they see any meaningful difference? Yes.
The orifice or the nozzles are the same.
They were the same. Yeah. Yeah. In one case, because one of the orifices was broken and we had to supply exactly the same one because we wanted the orifice to be the same. Yes, we considered that. We asked the operator if there was a meaningful drop in the pressure, in the suction power. And again, this is their feeling. We couldn't measure it, but they said that it's identical. It doesn't have a big impact in terms of, the drag force. And when it's in the big station, they reported that it was identical. But definitely when you can vacuum through the telescopic boom rather than an extension, it's the splatter would be more like less smaller. Let's put it that way. Yeah, it looked. And this is an effort. Look, the finding, again, the message, we only have to rely on air monitoring data. Whatever I'm explaining here was an effort to find a model to correlate something, to formulate something against our independent variables. But the main conclusion should come from the air monitoring data, full stop. Whatever I'm saying here was some statistical analysis trying to see if there is a relationship between those factors. we ended up having, look, when you do your factor analysis, look, the final product, you get few factors, and we ended up using 2 of them because they covered the majority of our variation. So the third one, if you check the report when it's published, the third one is too small to be considered significant. So we only had 2 factors that explain all variation in our model. And those 2 factors, you do some analysis and you find eigenvectors and all of things. I don't want to bother you with that. We ended up having 2 perpendicular factors, F1 and F2. Which one is F1? This is F1, correct? Yeah, this is F1, this is this is F1, this is F2. Anything close to F1 means the variation in that experiment was modeled or is described by that factor. And F1 is a combination of pressure, truck digging pattern. I think 60%, look, if you want to put it that way, 60% of F1 is digging pattern, 20% is pressure, 20% is, what was the third one? The truck. So a combination of those 3 with digging pattern being the most dominant explain these many of the experiments, these majority of our experiments. The rest, which are closer to F2, are explained by F2, which is again combination of pressure. Majority was digging pattern. This time the pressure and truck types was still to 2020, but negative and positive. So, but we know that those factors in combination have an impact. Individually, I will talk about the individual impact as well. But look, digging pattern, again, for your information, in the reality, in the real life, majority of the time when you use NDD, you do a trench. And trench, compared to the other 2 pattern, is the less concerning one. I don't want to use word safer. It's less concerning. Because when you dig down, it actually confines itself. The splatter is confined by itself. Look, individual impact, I told you, look, they work in group. But in terms of individual impact, the pressure itself, for example, when we switch from high pressure to low pressure in truck A, we had 10% drop in the maximum horizontal splatter. 2% decrease in vertical. So vertical was less sensitive in terms of the pressure drop. For truck B, these numbers were 15% and 9%. Comparable, but not significant as you expect. So when you drop the pressure in the range of 10%, you will have a smaller or bigger splatter. And again, horizontal splatter is more sensitive to pressure than the vertical splatter. Yeah. A weak but direct relationship between pressure and splatter, I've already explained. The range is 4.5 meters in terms of the size, if you want to have a rough estimate of the splatter size. Yeah, again, you see that the horizontal splatter, when we shift between, is this pressure? Yeah, when we shift between pressure, vertical is less sensitive, correct? Yeah, it's more uniform than when you apply consider horizontal splatter. Conclusions, and already moved 40 minutes. So contaminated soil, when we talk about contaminated soil, the liberation rates is manageable, okay? But the risk is still significantly high because you have cross-contamination and the contamination itself is challenging. Keep that in mind. Air monitoring data, all of them were under the 0.0 0.01 fiber per milliliter, the reportable threshold. When we applied it on ACM, numbers were significantly higher. So it needs a separate kind of investigation to understand what happens when you apply it on ACM. Cross-contamination is a big concern, the third findings. We have a model. Using that model, which with the pressure, with the type, with the excavation pattern, we can give you the an estimate of the size of the dust cloud. And using that, we ended up calculating the size and dimension of a shielding. So as long as, look, the problem is big, but the solution is simple. Thanks to John. John came with that kind of brilliant idea of testing the shielding. So with the shielding, it was effective, actually. We had air monitor and dust tracker behind the shield, and the numbers were like no concern at all. So keep that in mind. Shielding is an effective managed engineering safe, whatever, what we call it, an engineering response to that problem. It doesn't eliminate the risk. The asbestos would still be liberated, but it can be confined. So
What was the shielding? Was it geotextile?
We tried both. We tried plastic and geotextile. Both worked brilliantly. Look, not brilliant. It's over exaggerating. Equally good.
Over top of closure was just.
No, just around. Look, as long as it's there. Look, we tried 1.9 meter. It was tall enough to confine it, as long as with the typical excavation sizes. The good thing with the plastic was that it was easier to wash after the excavation. Geotextile, we washed it as well, but it's probably better to be replaced every time you use it. But the plastic, it was able to wash it. What else? Look, the same PPE and RPE still needs to be used, regardless of look, the risk is there. It doesn't mean that it's safe to just walk without any protection. It just suggests that it's manageable. We might kind of rethink about that regulatory ban. So it might be able to be managed effectively, but safety still, whatever required when asbestos, and Jason talked about the asbestos removal supervisors there. Look, everything that needs to be in typical situation needs to be there, applied there as well. While external decontamination of NDD truck and equipment, look, washing and wet wiping, like again, typical decontamination was effective where you had access. But because that vacuum circuit is a closed circuit, it's very difficult to reach out the interior and get a sample. So we ended up recommending that. And look, it might be a big economical look, we may work out the regulatory barrier, but set another barrier, economical barrier, because we recommended that you need to reserve that truck and the equipment just for asbestos work. And how big the asbestos business is for NDD, the anecdotal evidence is that it's big. Okay, it's big enough to justify that, but we haven't done a quantitative analysis. Part of this study, we did a qualitative analysis when we interviewed different stakeholders. They indicated that the market for asbestos, for NDD on asbestos contaminated work exists there. The potential is there, but we haven't done a quantitative analysis. So I can't really give you a number in that regard, but that might be a economical barrier which needs to be overcome. All right, look, thank you for listening.